Okay, guys, welcome. Today we're going to talk about inverse trigonometric functions. Okay, so we're going to talk about how to compute values of the inverse cosine, inverse sine, and inverse tangent functions. We'll also talk about how to locate the radius for the unit circle corresponding to these three inverse trig functions. Talk about how we can use these to find angles in a right triangle. Talk about how we can find the angles in an isosceles triangle if we are given the lengths using the inverse trig functions. And we'll also talk about how to use the inverse tangent to find an angle with a line for that has a given slope, right? So when we say that a function has an inverse, remember that in order to have an inverse, you need to be one-to-one. So only one-to-one functions have inverses. All right, and I should say only one-to-one functions have inverses. Now, of course, if you look at the graph of cosine, right, so this is y equals cosine of x. If you look at the entire graph, of course, it's going to fail the horizontal line test, right? If you draw a horizontal line essentially anywhere where you have graph for the cosine, you're going to fail the horizontal line test. Now, what we're going to do is we're going to restrict our cosine function to just sort of a piece that is one-to-one. Now, if you look at just this part in between these two x values here, so if you look at the interval from 0 to pi, so on the interval 0 to pi, cosine x is one-to-one. So if we strict it to just that interval, we get that the cosine is one-to-one. So we're going to, with this in mind, we're going to talk about the inverse cosine function. So we're going to talk about what is the inverse of cosine x. All right. Now, what we're going to then have is if we're given a t value, of course, that's between -1 and 1, right, then of course that will allow us to talk about the inverse, right? Because the range, so the domain of our cosine that we're considering, so for cosine, we're going to restrict the domain so that, again, it's 0 to pi. And of course, the range for cosine, regardless of what interval you're on, is -1 to 1. Now, we're going to talk about the inverse cosine, and that's going to switch these. You're going to have that the domain is now -1 to 1, and that the range is 0 to pi, right? Because that's what happens to inverse functions. You flip their domain and range. So if you have a number that's between -1 and 1, you can plug it into what we'll refer to interchangeably as the arccosine of t, or also the inverse cosine of t. And what's going to come out is the angle whose cosine would give you t, right? So it's going to sort of be undoing this process, right? So for cosine, you have an angle going in, and you have a number between 0 and 1 come out. Sorry, between -1 and 1. Now, for the inverse cosine, of course, the opposite happens. You're going to have number between -1 and 1 go in, and you're going to have an angle come out. And of course, in order for this to be 1 to 1, that angle will be between 0 and pi. Okay. And a sort of a nice, concise way of looking at this is that if you have arccosine of t equaling theta, that means that if you take cosine of that theta, you get t, right? And of course, to maintain the one-to-oneness, we just require that our angle is between 0 and pi. Okay, so let's think about this for a second. So in part A, we want to find the inverse cosine or the arccosine of 0, right? So we want to find what angle this is. Well, if we convert this to sort of the equivalent definition, this means we want to find an angle such that if I take its cosine, not that I get theta, that I get 0, right? So that's sort of what this means. Now, if you look at the unit circle, all right, where's your cosine 0? That's when your x value is 0. And this is a really terrible unit circle, but your two x coordinates being 0 are going to occur here, right? So you're going to have this occur at 0, -1, and this is, of course, 0, +1. So you're going to get two angles, of course, that give you a cosine of 0. You're going to get pi/2 and 3 pi/2. But again, we're only restricting our cosine from 0 to pi. So we're only concerned with angles that are on the top half of the unit circle. So this means that we want theta to be pi/2. Okay. Now, in part B, we want to find the inverse cosine of 1. And again, this will give you some angle to come out. And again, if you convert this, this means that we want to find an angle whose cosine is equal to 1. Well, where do we have a cosine of 1? Of course, that's going to happen here, 1, 0. And in this case, we don't even need to worry about picking one of the points. This only happens in one spot. We know that this is at theta equal to 0. Right? Now, part C, we want to explain why the inverse cosine of 2 doesn't make any sense. Well, as soon as you go to set this up in the equivalent form, we want to find an angle whose cosine is 2. But again, the problem with this is that cosine is only between -1, +1. So you're never going to get to 2. So this can never happen. All right, so you have to be careful there. And again, that just speaks to our point that the domain of the arccosine is all numbers between -1 and 1, okay? So that's how we can find each of those things. Now, here we're going to do an example just to show sort of that that you have to be careful of the notation here, all right? So the inverse cosine of 0.2 is part A, means that we want to find an angle whose cosine is 0.2. All right. Now, of course, you can just do this in the calculator. Right. And I'm going to assume that we're in degrees here. So all my answers will be in degrees for this problem. So if I find the inverse cosine, which you on most calculators would get by doing second and cosine, and if I type that in, I'm going to get that theta is roughly 78.46 degrees. Right, remember, so all these inverse trig functions will give you an angle to come out. Now, part B is asking for the cosine of x all to the -1, which means 1 over cosine of x, which in this case is, again, 0.2. All right, so now this is a completely different calculation. This is cosine of 0.2, and of course I need to do 1 divided by that. Okay, and then if I type that in, I'm going to get that this is 1.50, it looks like, and then a 6092. Right? So again, completely different answers here. And part C, I want to do cosine of 0.2 to the -1, which is cosine of 1 over 0.2. So now if I type this in, I'm going to get that this is roughly 0.996. All right. So just be aware that all three of these questions have different meanings, right? So don't fall into a habit of confusing those three. Okay. Now let's look at the next idea, right? So now we want to be able to find where is the radius in the unit circle that corresponds to an angle of the inverse cosine of 0.3. Well, again, this is some angle, and this means that I want to find the angle whose cosine is 0.3. Well, if I want to find the angle whose cosine is 0.3, again, you can do this with or without a calculator. Now, since we are looking at the inverse cosine, I'm only, again, looking at the top half of the unit circle. Okay. Now, where is x equal to 0.3? Well, if this is x equals 1, then 0.3 should be somewhere right about here. So then that means that this is the radius that corresponds to the inverse cosine of 0.3. All right, this is x equals 0.3. All right, and now if you enter this in the calculator, if you do the inverse cosine of 0.3, you get that the angle, all right, so this is in the calculator, you get that the angle is roughly 72.54. All right, so that tells you that this angle here is 72.54 degrees. All right, and that's sort of the idea. Okay, now this is just, again, reiterating the fact that your domain and range of arccosine is sort of the flipped version for cosine. And again, we just make sure that we restrict cosine to be from 0 to pi so that we don't have any double values, right? We want this to be a one-to-one function. Okay, now if we look at this word problem, we're supposing that a 13-foot ladder is leaned against a building, reaching to the bottom of a second floor window that's 12 feet above the ground. We want to know what angle does the ladder make with the building. So if we draw this out, and again, in all these problems, the idea is to try and get a right triangle involved. We know that this ladder is 13 feet, and we know that this height, I think they said was 12 feet. Yeah, 12 feet. Now we want to know what angle does the ladder make with the building, so we're interested in this angle here. Okay, now what's the relationship of my sides? Well, the 12 feet is my adjacent, and my 13 is my hypotenuse. So if I were to set up a trig relation for this, I would have that cosine of theta is equal to 12 over 13. But if I convert this to the arccosine form, then I have the inverse cosine of 12 over 13 would give me my angle. And this, of course, is something that we can find in the calculator, right? So if we enter this in the calculator, second cosine 12 over 13, and again, this is going to give me my answer in degrees. So we get that theta is roughly 22.62 degrees. All right. And of course, if you had your calculator in radians, you could get the answer in radians. But here I'm leaving it in degrees for now. Okay. Now, one thing that I will make a comment on as far as if you enter this in radians is that it will give you a gross decimal amount. So it's usually better for these problems to have it in degrees. And then if you want it in radians, just multiply by pi over 180, right? And then you can get the radians that way. All right, but that's how we can find this angle. Okay, so that takes care of the arccosine. So now we want to do a similar approach. This is now the graph of y equals sine of x. Now, its graph is a little bit different. And in order to make this one-to-one, we're going to consider it from negative pi over 2 to pi over 2. Right, so this we're going to view slightly differently so that we can account for sort of that shift that happens here. Now, what does this translate to? This means that for arcsine, if I'm looking at negative pi over 2 to pi over 2, I'm only looking at the right half of the unit circle, right? And the reason why I would do that is because I'm going to capture all the y values, right? The other side, I would get some repeats. All right, but again, a similar idea here with the arcsine. If I have sine of theta, right, that has, of course, this restricted domain is negative pi over 2 to pi over 2. And of course, its range is 0 to 1. Sorry, I keep saying that. Negative 1 to 1. Then the inverse sine, or the arcsine, is going to have these flipped, right? So its domain will be from negative 1 to 1, and its range will be from negative pi over 2 to pi over 2. Right? And this is sort of the analogous version of what we did for cosine, but now we're talking about for sine now. Okay, so let's do some examples of arcsine. So again, on the unit circle, we first want to evaluate the inverse sine of 0. And again, this will give me some angle to come out just like it did in the cosine case. Now this means that I want to find an angle who, if I take its sine, gives me 0, right? Or equivalently, I want to find where do I have a y value of 0. Now, of course, that happens in two spots, right? I get a y value of 0 here and a y value of 0 here. But again, since we're looking at arcsine, I'm only concerned with this half of the unit circle. I'm only looking from negative pi over 2 to pi over 2. Let me sort of forget this side. So of course, what point does this happen at? This happens not at a point, but at an angle of theta equals 0. Right? Now for part B, we want the inverse sine of negative 1. All right. So again, we want the angle who, if I take its sine, gives me negative 1, or I want a y value of negative 1. And of course, where does that happen? That happens here. So my angle is negative pi over 2. Now here, again, you want to be careful. You don't want to say that your angle is 3 pi over 2 because that's outside of our domain. We want to say that this is explicitly negative pi over 2. Okay, and part C, explain why inverse sine of negative 3 doesn't make any sense. Well, this is similar to before. If I wanted to find an angle whose sine is negative 3, this can't happen because sine is only between negative 1 and positive 1. All right, so this doesn't make any sense. Okay, now similarly, let's sketch the radius of the unit circle. This time, we're going to do it for inverse sine of 0.3. All right, now you can do this one of two ways, just like we did before. We can either enter this in the calculator, which we'll do in a second, but we can also say that this is the angle whose sine is 0.3 or whose y value is 0.3. So on the unit circle, right, we know that this is a y value of 1, so y value of 0.3 should occur right here. And again, since we're dealing with the arcsine, I don't want to do anything on this side, right? I just want to look at negative pi over 2 to positive pi over 2. All right, so I'm going to be concerned with this radius right here. All right, now if we enter this in the calculator, we could get what that angle precisely is. So this would be found by doing second sine. If I do 0.3, I'm going to get that this is a 17.46 roughly. So we get a 17.46 degrees in there. All right, so that looks reasonable. All right, so there's a couple different ways that you could sort of find that radius. Okay, and of course, this is stressing the idea that if I want the domain of the arcsine, that's the range of sine, which is negative 1 to 1, and then our range of sine is our restricted domain of sine, which is negative pi over 2 to pi over 2. Okay, so another sort of application type problem. We're going to suppose that our altitude goes up by 150 feet while driving 1/2 of a mile on a straight road. We want to know what is the angle of elevation. So what's happening is that we have, and here they're sort of setting us up as a trick here, right? Because this is 150 feet, but this is 1/2 of a mile. And we need to find this angle. But we need to make a decision, right? Because our units are different. So we either need to convert feet to miles or we need to convert miles to feet. Well, we can use the fact that 1 mile is 5,280 feet. So if I want 1/2 of a mile, I need to take 1/2 of 5,280, which should be a 2,640. So this is 2,640 feet. All right. Well, now what's the relationship of these sides? This would be, wait a minute. So I guess what we would then need to say is I actually, if the road is up here, it's not my horizontal distance. The length of the road should actually be up here. Can I move it? All right, so I actually want this to be here because the length of the road would actually be the hypotenuse, right? So 150 feet would be my opposite side, and this would be my hypotenuse side, right? So then I could say that the sine of my angle is 150 over 2,640. And then if I convert this, I would say that my angle is the inverse sine of 150 over 2,640. So then if I type this in, so 150 over 2,640, we get that the angle of elevation for this road is about 3.26 degrees. All right, and I should put the roughly equal to there. All right, so you get that this angle is roughly 3.26 degrees. So that's how we can use the inverse sine function in sort of like an application type of problem. Okay, now can we extend this to a non-right triangle? Well, let's take a look. So we want to find the angle between the two side lengths of 7 in an isosceles triangle that has the other side length 8 and the two sides are length 7. So we have something like this. All right, so if these two are both 7 and this is 8, and I want to find this angle here. All right, well, here's what we can do. Well, we know that this is an isosceles triangle. So if I cut this bottom side in half, then I don't necessarily have this is 8, but I have that this is 4 and this is 4. All right. So then what we can do is if I find this angle, then I get this angle for free, and then I can figure out the top angle. All right. So what I need to do off to the side, let's maybe try and draw this a little bit better. Okay, that's a little bit better. If this is 4 and this is 7, I want to find what this angle is, right? And then once I have that angle, I can double it, right? So if I have that as my angle, then 4 is my opposite side, and 7 is my hypotenuse. So I know that the sine of theta is 4 over 7, so theta is the inverse sine of 4 over 7. Right, and I mentioned earlier that you could also find this angle. So in this case, if I wanted to find that angle instead, I would use the inverse cosine, right? But you know, this will actually work quicker. I didn't realize that right away. But if I take the inverse sine of 4 over 7, we get that our angle is roughly 34.85. But remember, we wanted this entire angle at the top, and we just found 1/2 of it, right? So therefore, the angle between the two 7 sides of length 7 is going to be 2 times theta, which is 2 times 34.85. And if I do that, I'll get that this is a 69.7 roughly. All right, so that angle between those two sides of length 7 would be 69.7 degrees roughly. Okay, so that's how we can use the arcsine. Now again, just for what we needed to do for arcsine and arccosine, we also need to restrict our tangent function so that we have something that's 1 to 1. All right, now this is the interval negative pi over 2 to 2 again. Pi over 2, I mean. Right? And of course, you have that those green lines are asymptotes. So if we go from negative 2 to pi over 2, we technically wouldn't even include pi over 2 in our analysis, right? Because we get something that's undefined there. Right? So that's where you're seeing the parentheses here, right? You want to go from negative pi over 2 to pi over 2, but don't include them because you have that the tangent is undefined there. All right. Also, one thing to note here is that your tangent has a domain of all real numbers, right? And of course, your range is, sorry, your domain, yeah, your domain and your range are both all real numbers, right? Now, your domain will exclude odd multiples of pi over 2. And of course, on this restriction, we're letting our domain just be negative pi over 2 to pi over 2, non-inclusive, right? So then your range, or I should say that your arctangent will have a domain of all real numbers and a range of negative pi over 2 to pi over 2, non-inclusive. Right, so that's sort of what's going on here. So just keep in mind that the arctangent is slightly different sort of analysis than for the arcsine and arccosine. Okay, but let's take a look. So in part A, we want the inverse tangent of 0. So again, this is going to give you some angle, and in particular, it's the angle who, if I take its tangent, would give me a 0. All right. Now, what you can do here is you can remember that you can remember that tangent is sine over cosine. So if sine over cosine is equal to 0, that means that sine is equal to 0. Okay. And again, between negative pi over 2 and pi over 2, where sine 0, this happens at an angle of 0. Right? Because if you look at your unit circle, and again, we're only concerned with the right half because of our restricted domain. Sine is 0 here. Right? Now in part B, we want to know what is the inverse tangent of 1, right? Which again means that if I want to find an angle whose tangent is equal to 1, or I want to find when sine over cosine is equal to 1, which I can then cross multiply and say that sine is equal to cosine. All right. Now, where is sine equal to cosine, or where is x equal to y? By now, we know that that is for your 45-degree angle or your pi over 4 angle, right? Because that's where they're both square root of 2 over 2 for both x and y. So if this, of course, this happens when theta is equal to pi over 4, or you could say that that's 45 degrees. All right. Now in part C, we want to find where is the inverse tangent of square root of 3. So again, this means I want to find an angle whose tangent is square root of 3. So I want to solve when is sine over cosine equal to square root of 3. Now for this one, we'll use a little bit different of a technique. All right, in the last one, it's easy to see where's your sine and cosine equal, but in this case, we have something like sine is equal to square root of 3 cosine theta. So now here we can use cosine squared plus sine squared is equal to 1. And if I plug in, so I'm going to say cosine squared plus sine squared, which I'm going to say is square root of 3 cosine squared. So this gives me a cosine squared plus a 3 cosine squared is equal to 1. So when I combine, I'll get cosine squared is equal to 1 over 4. So then I'm going to get that cosine is equal to plus or minus 1/2. Right? And if my cosine is plus or minus 1/2, then we can use this relationship here to say that sine would have to be plus or minus square root of 3 over 2. Now, again, what was the original problem? The original problem was we needed to find the inverse tangent, right? Now, if I'm looking at the inverse tangent, I'm only on the right side of the plane, right? So what I would need to do is that if I'm on the right side of the plane and my tangent is positive, and in this case it is, I need them both to be positive. So I would need when sine of theta is square root of 3 over 2, and when cosine is 1 over 2, right? So of course, this is when you have a 30, 60, 90 triangle. Draw this a little bigger. Of course, this is not drawn to scale, but let's say this is my 30, this is my 60, and this is my 90. So across from my 30, I would get the 1/2, and from my 60, I would get the square root of 3 over 2. Right? So where do I have an adjacent side of 1/2 and an opposite side of square root of 3 over 2? That happens for 60 degrees. So my theta is 60 degrees, or we could just as easily say that that is pi over 3. Right? So either one of those two would work. All right, so a little bit more work for that one. Okay. Now in example 10, we want to sketch a radius that corresponds to the inverse tangent of -3. So I want to find the inverse tangent of -3, which again means that I want to find an angle whose tangent is -3. Or we could just as easily say y over x is -3, which is to say the line y equals -3x, right? So in this one, and this is going to sort of segue us into our next conversation, but what does the line y equals -3x look like? That means that I would want to start at 0, 0, because I don't have a y-intercept, and I want to go down by 3 and over 1. So I'm going to get a point somewhere over here. Right? And as long as this is the line y equals -3x, then this is the radius that I'm concerned with. And again, I don't care about the left half because inverse tangent just goes from minus pi over 2 to pi over 2. And that would be my corresponding radius. All right, so that's the radius for inverse tangent of -3. All right, so just to summarize, there's my domain and range for each of the 3 inverse trig functions that we talked about. Okay, now we're going to do a right triangle trig problem. So in this right triangle, we're going to use arctangent to find u, right? Now the tangent of u is equal to 5 over 9. So that means that u is the arctangent, or the inverse tangent, of 5 over 9. And if we let our calculator do the work for that, we get the inverse tangent of 5 over 9, that u is going to equal roughly 29.05 degrees. okay? Now to find the angle V, I would do something similar. That would be the inverse tangent of now 9/5, because now opposite over adjacent would be 9/5. So if I do that, we get that this is roughly 60.95 degrees, right? And of course, part C, so this was part A, this is part B. Part C is to verify by adding these. And of course, if you add these, you do get 90 degrees, which is what we should expect. All right, so that's how we can use the arctangent in this case to find some triangle angles. All right, and then last but not least, so last but not least, we want to know what angle does the line y equals 2/3 x in the xy plane make with the axis? Well, here we can use the fact that I'm looking at a triangle with a base of 3 and a height of 2, and here's my angle, right? I want to find what that angle is. So I know that the tangent of that angle is opposite over adjacent, so 2/3. So my angle, once I convert, is going to be the inverse tangent of 2/3. So then if we type this into the calculator, we can get our angle, and the angle 2/3 is going to roughly be about 33.69 degrees. Okay, so this is a nice introduction to the inverse trig functions. I hope you enjoyed, and I will see you next time.